Welcome to MACSMIN 2025. I hope online participants can hear us. It's a great pleasure to introduce Dr. Daniel Widdowson, who will talk about his Crystal Geomap based on our invariants. So please, Dan.
Thank you. All right, so there's going to be a fair bit of reintroduced content around the start, which will be a little bit more boring, but then it should get more exciting towards the end with some pretty pictures. So we'll enjoy that. I can't get rid of this thing from Zoom at the top, so it'll have to go. Yeah, I hope so. So this is supposed to be about my geomap, but that will be a demo for the end of the talk. I suppose I have to really introduce the reasons it's here, right? Which will be a lot of what we've heard already. But let's start here with the slide I like. So the definition of crystal, according to the International Union of Crystallography, is this sentence. A solid is a crystal if its atoms, ions, molecules form, on average, a long-range order arrangement. Nice sounding definition for English, I think. It was arrived at through a lot of debate and just time for crystallographers disagreeing on what the definition should be, but they finally settled on something, except they didn't, because this is one of two definitions, which is on the dictionary. So they sort of got there, but it's not very precise, right? This is probably intentionally quite loose because a precise definition is kind of hard to give. You'd like to say it's periodic, but well, we now know that some crystals aren't periodic, and you can't even use disorder to describe some things that we want to be crystals. But anyway, even given this nice definition of crystal, crystallographers are asking the question, well, yeah, but which crystals are really the same crystals and which ones aren't the same crystals, right? So we're going to come at this problem with mathematics using formal definitions of, so we'll start with periodic point set, and then we'll go to this crystal isometry space. So it's the moduli space of crystals up to isometry, we'll get there. And then we essentially put coordinates on this space. And the idea is you walk around the crystal space and your coordinates smoothly change as you're smoothly perturbing atoms in your crystal. But let's start with just definition of a periodic point set. So my mouse be seen, yeah, I'm sharing screen. So start with a linear basis. Here it says of R3. That is the case with real crystals, but these definitions work in any dimension. So we start with a basis, it defines a parallelepiped, so this box, and then you put some points in the box. These are representing your atoms. So for now, we're not going to bother listing the atomic types. We can add them back in later to see what happens, but we're just focused on geometry. So we're going to upset some crystallographers already with that. But as Vitaly sort of alluded to, you can get by with geometry, or get a lot of the way with geometry. So here we've got definition of a periodic point set, and the lines are just there to sort of help you intuitively, right? The object we're talking about is this infinite set of points that repeats according to this basis. So the problem we're trying to solve is ambiguity, right? So this periodic point set, or any of them, could be represented by infinitely many choices of cell and motif. So cell and motif is a very natural, intuitive way to define your periodic point set that you have, and it's the one that's used, but there are many different ways you could do that. So, and I think they realized this a while ago and came up with things like cell reduction. So on the left here, we have many different cells that define the same lattice here. You can reduce these cells and get back to the original one, but it's not fully sufficient for reasons we'll get into. I mean, if you add this motif in here, see that we can define the same periodic set with the same cell, but just chosen in a different place. So there's like a big broad strokes of ambiguity here that we want to kind of resolve. So the first equivalence we're going to have to introduce, I suppose it will be the only one for my talk, is isometry. So obviously a crystal doesn't change when you take it and apply a translation or a rotation to it, because crystals are rigid objects. And we want to identify them as such. Two crystals which are simply represented differently, but are literally identical down to everything, should be considered the same. So we're going to try and solve this problem with an invariant. So yeah, rigid motion, whoops, where am I? There we are. Rigid motion is the best equivalence, I suppose, the most strict best equivalence on periodic sets. Reflections give us a slightly weaker class of, it's a slightly weaker equivalence. But if you require that you want to distinguish between reflections, the mathematics gets a little bit muddier and it's more expensive. So there is something to be said for sacrificing the fact that you can't distinguish reflections in order to get a lot of like speed out of your invariant, which is kind of where we're sitting, just below this completeness. Anyway, we'll get there. So let's define this crystal isometry space. This is going to be one space where each object is a crystal up to isometry. So not one particular choice or representation of your crystal, but all images of that crystal, the ways that it could be represented. In general, an equivalence relation is a kind of a function that takes two objects in a space and says they're either equivalent or not. And an equivalence relation satisfies three rules. The three rules are written up here. But the important part is that it takes a space of objects. In our case, this space of objects is the space of all periodic sets. So it could be any choice of motif and unit cell, right? And different objects, even though we want them to be equivalent, could be chosen with different motifs and unit cells. So in the space of periodic sets, they live in different places. We need them to be the same thing. So the equivalence relation splits that space up into chunks where everything in the same chunk is equivalent and everything in different chunks are all non-equivalent. So for us, the relationship is isometry. Isometry, so if a crystal is always isometric to itself because the identity transformation is an isometry. And isometry works back and forth, so you have symmetry, and then this is also satisfied by symmetry. So this space of periodic sets, when you put isometry on top of it, it gets split up into all these disjoint classes, and each class is one crystal for us, one periodic crystal up to isometry, we could say. So we have this nice definition of this space containing crystals, and what we want to do is parameterize this space well with certain conditions so that we get nicer results out of it. So let's introduce what an invariant is, I suppose. So we're looking for a property where we can plug in our periodic sets and get out something through this machine, or let's say I is the name I've given to the function here, and that's going to have to satisfy certain things. So the most important one is that equivalent periodic sets get the same invariant or same property, and then we can call it an invariant. And this is very important, I guess. It's so important that I can't really think of too many non-invariant values, but you can think of something like the center of mass of a motif in a unit cell, which you can shift. And I think everyone basically agrees that things that are non-invariant, they're not very useful. So this is where we start. And this isn't even a requirement. It's more like asking the function to be well defined on crystal space. So invariance, which has been introduced probably better by Vitali, is the first requirement, and we'll go through all of these. So completeness is the complement to that. I would say it's harder, but technically you can trivially construct a complete invariant. But for what we want, completeness is harder, and it means that if you gave me an invariant and you gave me an invariant and they're the same, for a complete invariant, I know that the original crystals that you had are the same as well. Whereas for something like density, maybe you give me a density, you give me a density, they're the same. Well, I don't know. They could be the same crystal, they might be different, who knows, right? But for a complete invariant, you know that if the outputs are the same, then the inputs were the same. And this kind of would constitute a kind of fingerprint for our crystals. So this would be very nice. It turns out it's difficult to do this with our other requirements. So probably more important, or something that we have as a requirement rather than this completeness, which we're trying to sort of edge towards, is continuity. So perturbing atoms in our structure or points in the periodic set, even if it breaks the symmetry, or if you extend the unit cell and then move stuff so that you can't reduce the unit cell back to its original thing, we want this to result in a smooth perturbation in the output rather than jumping. So in this case, the symmetry, the space group, say, of this crystal on the left is different than that of the right, even if you reduce them. So the smallest of perturbations has instantly gone from one group to the next group, which is bound to happen for discrete classifications, but it can also happen for non-discrete classifications. Well, we want continuity. So basically, if you can superimpose the two periodic sets on top of each other, you can imagine superimposing this one on this one, and then each atom will have only moved a little bit. So we want our the distance between the invariants of these things to be sort of bounded based on how much we moved the atoms by. And this is this continuity. It basically means that, let's go back a bit. Maybe this crystal space thing here, if you walk around it, then you're smoothly perturbing atoms and vice versa, right? That's the idea. Okay, so the full list is right here. We also do require a metric, which has been introduced a few times. If you don't have a metric on this space, mathematicians don't like that because things start to not work very well. Clustering gets a bit suspicious. So we also require a metric, and ideally we'd like it to be computable. And this is really the one that makes completeness difficult, I would say. We've constructed complete invariants, but they're expensive. Too expensive for 1 million crystals, which are really complicated. But you can get nearly all the way to completeness and be very, very well computable and handle tens of millions of structures still. So that's sort of where the things I'm going to introduce are living. And here's an image which sort of sums up what's going on. We've got 4 structures here. I mean, I've represented a structure here by a finite collection of points. These are all equivalent, right? I've just applied a reflection or translation, rotation. So they're all grouped together in this thing that's representing our crystal. And then they should all these things should map to this same point because they're all the same thing. That's what isometry invariance is. Then conversely, this other thing over here is not the same as those guys. You can't rigidly map it onto them. And so we want it to go to another place. That's completeness. Then over here, this gradual perturbation should result in like a smooth path in the space on the output. So this is a nice sort of pictorial summary of those requirements. So now I will introduce the PDD and later a few other invariants, and then we can get to results and then pictures. So yes, so I've got a real crystal here from the CSD, ethane 01. And the construction of PDD is relatively simple, I say. So you do this for each atom in the unit cell. Just start listing distances to its nearest neighbors. So for this carbon atom over here, I know it's outside the unit cell, but it's translationally equivalent to one inside, right? Its first distance to the first hydrogen will be 1.096, and then it's got the 3 other hydrogens around it, and then the closest carbon, and you just take this list. It could go on for forever, to infinity, because we don't stop at the unit cell boundary or anything. We just keep listing distances in the whole periodic set. And you do this for all atoms. So you could take these lists on infinitely, but obviously you can't do that in a computer. Instead, we choose some number k, a cutoff. I think in this example, I choose 10. Here I've listed 4 distances, right? But it goes on. So there's one parameter here, which Natalia likes to remind people is more like a decimal places on an approximation rather than something else where a parameter might change your invariant. It doesn't really change our invariant. It's more like a better and better approximation when you choose larger values of k. So the first step is to list these distances to neighboring atoms for each atom in the unit cell. Then you collect them all into this matrix. I've gone up to the 10th distance here. And yes, when 2 rows are equivalent, if they're the same, then you collapse them. In this case, there's a lot more than 4 atoms in this unit cell, but because of symmetry, obviously, there's only 4 symmetrically unique atoms. So this all gets collapsed into just 4 rows, each with equal weight. So the first one obviously corresponds to the carbon because it's got the 3 distances to its neighboring hydrogens around it. And then these other ones here are the 3 hydrogens.
Question, but why don't you use the asymmetric unit?
We do. It's just easier to explain that you use the motif, right? And then you can prove that the asymmetric unit works, and it's like a shortcut. Yeah. So, yeah, it's the equivalent. Yeah. And then finally, after you've collapsed according to thing, which actually, as you said, you don't actually usually have to do that because, well, unless the only thing breaking symmetry is the atomic type, then things collapse. But in the CSD, for example, you basically never end up collapsing this matrix because you use the asymmetric unit to start with. Yeah. And then after that, you apply ordering. You actually kind of don't have to do these because of how the metric works. But if you want this statement of isometry precisely with the equal sign, then you do have to apply this stable ordering. And then that's the PDD. It's a weighted distribution of numbers. Okay, so an example we've already seen, the PDD already shows that it's worth something at least. These two sets are difficult to distinguish otherwise with a much easier thing like just taking the distances and sorting them. But when you arrange them into this, the differences of the set, the relative differences between environments of the points become clear. I mean, one reason there's 2 rows up here and 3 down here is because of how the symmetries work, right? Here we've got 2 pairs of symmetrically equivalent points. Down here, we've got 1 pair of symmetrically equivalent points related through this mirror reflection with invariant points on either side. So we get a very different distribution, and PDD easily distinguishes things like this. Yeah, okay. So I'll try and explain a little bit how EMD works. So I've taken this crystal here. This is called T2 gamma in my mind, but it's a DebXIT01 from the CSD. We take its PDD. Now, there are 92 atoms in the motif, but only, how many is that? 11 in the asymmetric unit? 1, 2, 3, 4, 5, 6, 7, 8, 10. Yeah. So 10 atoms in the asymmetric unit. And here I've only chosen k equals 2, so we can plot it on 2D axes. And these distances as pairs can be plotted onto this plot over here. So this collection of points is kind of representing our whole crystal, although we've only chosen 2 distances, so it's a kind of bad PDD. But for this purposes of explaining how to compare PDDs, I've chosen a simple one with k equals 2, and then we get these points over here. So what happens if I apply a slight perturbation? Well, here's another ref code from the CSD, which is the same crystal. It's just been measured twice under, I guess, maybe slightly different conditions, or it's just been measured twice.
Temperature.
Are they slightly different temperatures? I'm actually not sure, but yeah, probably are. And you can see that the points just move slightly, right? So what EMD essentially does here is it says, well, we've got one set of points, the blue ones, and we've got the set of crosses, the orange crosses, and we're going to just pair up the points with the crosses, right, in the way that's completely natural. You can see here that all the weights attached to these points are all equal. So EMD in this case just says, oh, we can just pair up all these, and the total EMD here would be, so say this weight is 0.07, this cross. If you take the distance between that cross and that dot, multiply it by the weight, 0.07, and then add that up for all of the pairs of points, that's the EMD. And it changes continuously, right? Because if you apply a very, very small perturbation, the resulting perturbation on here will be very, very, very small. And everything's just nice and continuous. And this even works when you break the symmetry. So there's no example of this with broken symmetry in the CSD, so I've manually constructed one where now all of the 92 atoms, or I think it's 92 in the motif, are all unique because I've just perturbed them all in a random direction with no regards for symmetry. And now it's broken and it's a triclinic, I guess. Well, it's much lower symmetry anyway. And what's happened is the blue points have split apart into many orange crosses instead of just being one orange cross. But the EMD just kind of takes care of this because it will match up these single blue dots with the many orange crosses surrounding it. If you look at this, like this over here with weight 0.13, the total weight of all the orange crosses there will be 0.13. And EMD accounts for that. It doesn't have to be a one-to-one matching of these points. It can match up this one blue dot to many orange crosses around it. So I have an analogy here of like warehouses and shops. So you can imagine that the blue dots in the previous slide are like warehouses that have an amount of stock. That's their weight. And then you have the shops around them, which are kind of like the orange crosses. And they have a demand. we just say for our purposes, which is true in our case, that the total amount of goods in these warehouses equals the amount in the shop. So they need to all be supplied. And then the question is, what's the minimum cost of supplying all these shops, right? And for that, you need a distance or a cost per unit between each warehouse and each shop. So in that case, for our case, it's just the distance between a blue dot and one of the orange crosses. And all those distances are small for the little clusters that we've got, right? And so you add up all of the distances between the dots and the crosses and multiply them by the weights, and it all just changes continuously. Even if you break symmetries and stuff like that, it takes care of the situation very nicely, actually. Right, so let's go through some, there's a lot of text on this slide, but let's go through some of the properties. So obviously PDD is an invariant. If it wasn't, that would be a bit strange because I spent time introducing it, but yeah, it's independent of your choice of cell and motive, and it's invariant, and it's continuous. As I explained, when you put Earth mover's distance on top of it, you get a nice statement of continuity, even if symmetries break or whatever. We have quite a decent theoretical runtime, almost linear, right? In the M, the number of motive points, and K, which is the number of distances you go up to, kind of like, yeah, K is the number of distances. This is quite good, but maybe more importantly for experiments, it's quite good practically. So if someone were to ask me like, how many structures would be impossible? How many structures can it handle? I would probably say, well, how many can you store? Because it would take maybe, I don't know, it takes maybe an hour or two to process all the crystals I can find throughout the CSD and all these other really big databases. So unless you have 1 trillion crystals, even then, I think you'd just be waiting maybe a week or two. It's really not a problem, practically speaking, about 1 millisecond per structure. Obviously, it's not very difficult computational things. It's just distances between points. And then we have this result of generic completeness, which will be covered in the next slide as well, which basically says that PDDs are very good, theoretically, at distinguishing structures, although not perfect. So this is what the conditions of generic completeness look like. I'm not going to read them out. I'm just going to say that it basically prohibits certain singular situations which are really annoying when you could try and go and reconstruct your original crystal from the PDD. So these conditions, if they are satisfied, mean that you can reconstruct from PDD and you do have completeness as well. But if they're not, then you don't. And these conditions, while they might look restrictive somehow, they make up the subspace of crystal space for which these conditions are false is measure 0 in that space. Right? So actually 100% of the crystal space is completely distinguished by PDD. So this is a nice theoretical result, right? Okay, and now I better take time to introduce this. So a much simpler invariant can be obtained if you just take this PDD and take the weighted average along the up and down, right? So I'll just, if you take the average of all these first 4, obviously you just get this. If you average the second column, multiplying by these weights, then you get this, and you just get this vector, which is simpler to carry around, faster to compare. So we often still use it because the EMD algorithm, as you can imagine, it is a somewhat complicated algorithm. I don't understand the implementation of it that I use, to be honest, and it's a little bit expensive. Not compared to something like COMPACK, which takes like 1 or 2 seconds. We're talking about more like a few milliseconds, but AMD is a vector, and computers are just crazy good at vector mathematics. That's like what they're designed for, right? So it's very, very quick to compare these AMDs, and it still finds its use. And it's still very strong. It's enough to distinguish vast majority or all actual real periodic crystals in the CSD, as far as we can tell. Okay. Yes, so a few more results. So we found out via just literature that was laying around that the distances between AMD and PDD are related by this. And this is actually an EMD result. EMD is a classical metric that it predates certainly me or probably this research, right? But this holds for any EMD. Actually, the AMD is, in statistical terms, it's considered the centroid of the PDD. And it just turns out that the distance is bounded like this. This is actually quite nice because it means you can test AMD first. And if the AMD distance is really big, you know that the PDD distance would be even bigger. So there's no point in testing the more expensive EMD distance. You can sort of do this filtering. And if you really wanted to with a big set, you could put a filter before AMD like density, right, or point density. But this already is introducing this hierarchy of invariants where you go to more strong invariants and you only have to use the stronger invariants on the crystals that were close enough in the previous round. We know what these things converge to. So if you just plot what I've shown you so far, the AMD, what you'll see is a cube root-like curve. Obviously, the distances just go up and up and up and up onto infinity, but they very specifically converge to this thing where Vn there is the volume of a n ball, a unit n ball. M is the motive points and volume of the unit cell there. So this this first term underneath the nth root there without the nth root k, that we call the PPC. That might be relevant later, but essentially we have completely described the asymptotic behavior of these things, which is nice because it turns out to be much better for plotting. And we've given an extra name to the result of taking AMD and then subtracting its asymptotic curve. So now what you're going to get, instead of this cube root thing that just goes up and up and up, when you subtract that asymptotic, you get this sort of wave-like thing. And I'll show some pictures of that in just a second. And as Vitali mentioned, some of our experiments, some from a while ago, and then they've been updated and we found more. We compared all the crystals we could find for weird stuff. And we found stuff that was, identical and wasn't really supposed to be. We found things which were errors. At first, this one down here, I thought was a CSD error because the published paper has C11 and then it's become CL1. Looks like it's conclusive to me, but I'm not a chemist. So we asked the CSD, the CCDC guy, and he said, no, we're actually right. We corrected that. It was the original author who was wrong. So it turns out that it's the COD entry, the Crystallography Open Database. Their entry is wrong, but there is no action to be taken, I think, because the COD curators don't care about the information being correct. They care about it being the original published information. So I think that's going to stay the way it is, but we found it. Okay, and then a brief detour for 2 slides. So briefly introduced by Vitali was the higher order PDD. So there are still examples where PDD fails to distinguish genuinely different structures. And we've got an example here. This is families of structures, of pairs of structures, a big family, where you can choose your parameters and get a pair of structures that PDD can't distinguish. There's just not enough information there. Which is hence generic completeness and not full completeness. So we were motivated to extend the idea of PDD to include more information. So instead of measuring, this is also ethane N1, by the way. I've selected a atom here. In the PDD, I would go to the nearest neighbor and measure the distance, the next one, the next one, the next one. In this case, we're going to look for pairs of neighbors. So there I've drawn a little triangle with 2 neighbors there, and we get this infinite triangle. So this would be the 2nd order PDD, where we look at triangles. 3rd order PDD, where we'd look at tetrahedra. So H order PDD considers H simplices. The simplex has to include this point that we're considering, and then you order those simplices by their perimeter, or their average perimeter, basically. And you get something that looks, the shape is exactly the same as PDD, but it should contain a lot more information because we've gone ahead and sort of, well, I don't know if I can just justify on the spot why it contains more information, but it certainly does because we have the results to prove it. So this does distinguish the periodic sets on the left. Simplices should contain more information than single distances, right? And yeah, so this construction is actually similar. And of course, I should use my arrow keys. So we are mathematicians, and I'd hate it if this PDDH didn't extend PDD, but it does. So PDD1 obviously is one simplices, it's just a line, and this naturally extends it, and we have a nice result here, which is very similar to the result we have for PDD. And then we have different notations, so you can actually concatenate or combine all the PDDs up to H, and then you get like one big invariant, which is very distinguishing. And we haven't found any counterexamples to incompleteness for this thing yet. So we conjecture it is enough information to completely determine everything up to isometry. And then we have a nice conjecture about the equivalent of the asymptotic thing that we have. We've proved it for PDD and AMD, but in the case of this higher order PDD, the coefficient here, this root k, it was nth root of k. Now it's a bit more complicated, but we suspect that each choice has its own sort of PPC depending the I guess S and H here. So there is an equivalent asymptotic, but we haven't proved it. It's just conjectured. And then down here we have a very long statement about time. A and B here are parameters which are not particularly interesting. They're kind of large, but there's no exponentials in there. The most important thing to look at, I think, in this case is that if you fix H and you fix N, then you have no exponentials in there. It's still relatively good, despite the long equation inside the O there. And practically for these guys, actually, they're still pretty good most of the time. In my experience, it's just a few structures, and I don't know which ones they are, and I don't know why they don't like me, but they just take a long time. But most of them are actually pretty good. It's harder. Sorry.
Big O notation, different terms, strange to me. Is it because it's basically different big O notations in different variables? Because usually,
So
these are from different steps of the algorithm to produce the PDD, aren't they?
what does big O mean?
what's in infinity, right? If one of the parameters goes to infinity.
So it's a constant times flow function.
Yeah.
So up above. Okay, yeah, have an expert.
Yes.
Janusz. So
Constant.
They should just try to figure out if what parameters are called, since they are.
Well,
But usually you would think one term dominates in the. But this is because.
I think I see what you mean.
Because it's written for different parameters. Yeah. Different.
I think there are multiple parameters, so you can't. Each term could dominate depending on the parameter you're changing, I guess.
Okay, you're right. So strictly speaking, we should have written it with a constant, such like the number of operations is not greater than a constant times the function in the brackets. Yeah, this would be a more rigorous.
But I think you're saying usually you don't see sums inside big O notation, because if it was like a polynomial, then the largest degree would just dominate and you could get rid of the other stuff. But in this case, maybe any of these terms could dominate depending on, like this has a to the hn, right? If you depends on what you fix and what you don't fix.
That's meant because it's basically multiple.
Yeah, I think it's
in one. And you could have different terms that dominate. Okay, thank you.
I guess so. Yeah. So not terrible, not as pretty as the other bigger notation, but it is what it is. Okay, so now we get some pictures. What am I like on time? Okay, good. So this is actually what this coordinate or this AMD looks like. I've taken the AMD, which itself is this cube root thing, and you subtract that asymptotic and get this ADA. So it's this kind of sound wave looking thing where these peaks and troughs are corresponding to voids and denser areas in the structure. And I really like this image because we've got two pairs of crystals here. So the CSD ref code family will tell you that this first one and this third one are using the same molecule, and so are the second and fourth. The molecules are similar. They both have this tripod shape, and they compact in similar ways or crystallize in similar ways. So this Eurofop is, you see that the molecules have all decided to arrange themselves similarly to this DebXITO one. And that has come through in the AMD or the ARDA here. You can see a big deviation at the start of these curves. That's because the molecules are different. So if in like very local terms, for looking at just like nearest atoms within the same molecule, for instance, the molecules are very different. So you get a big deviation at the start here. But then you look at higher and higher K, and suddenly you see that they're very much agreeing with each other in quite a nice way. So AMD really captures a lot about geometry, not only like precisely from atom to atom, but also sort of generically. So this is quite a nice way of depicting what a crystal's coordinate looks like. And from here, we're not going to see plots like this, but more like plots of the entire crystal space or universe, something like that. Okay, yeah, I have a few slides here I forgot about, but let's go through them. So if you're not familiar, a while back, Google tried to start the process of synthesizing new crystals completely in silico, something like that, using a bunch of AI. So in 2021, they took a snapshot of the ICSD and materials project to Crystal databases, and they wanted to train this AI called Genome to try and find new materials. A couple of years later, they published their results. They say they have millions of crystals back there, but they only released a few to the public. I say a few, it was 400,000. And then they created this autonomous lab, a lab, which targeted certain crystals which were manually selected and tried to actually synthesize them completely autonomously. So the idea is that you go from start to finish with no human intervention. It's quite a good goal, I'd say. So this autonomous lab managed to synthesize quite a good proportion of them, and with intervention from humans, a few more. But then years later and the years since, papers have come out saying that these results are not so great necessarily. So some of the rebuttal papers are just saying that the data is bad and we're not sure that you actually synthesized what you said you did. But when we looked, we found that all of these crystals just exist in the databases that it was used to train the AI before this even started. And one of the problems was that it was repeating structures, but using different representations of the structure. So like here we have two from the ICSD, and yeah, the left one was predicted by GNOME, and then they went, yeah, that looks like a good crystal. We'll get ALAB to synthesize it. But it turned out these just existed already. So with all this talk of like uniqueness, because the genome paper stressed that new things needed to be unique and new, right? Or else there's no point. The AI is just spitting out the same thing you already know. So they had some criteria to decide what's unique, but what was it? Well, we draw what the unit cells are here. Sorry for the red line, but I hope you can see the unit cells are very different. These two aren't too different, but there is a perturbation there. So when these were compared with, when the output of the AI was compared with the stuff of that was input into the AI, they didn't find this match. Well, it's a lack of technology because they didn't know. They ran it through the algorithm and it said, no, there's no matches because they didn't know it's a different space group and they used the space groups. So, and by the way, if you ask the AI to do something unique and there's a way of tricking you, then it's going to try and trick you to get a good answer. And so this is like a problem that you need to address, right? Yeah. So we found that like all of these crystals that they had apparently found actually pre-exist. Some of them go back like 70 years. I think the oldest one is from like 1960s or something, and they rediscovered it. Yeah. So yeah, we found a bunch in the training data set, and they all have isometric logs, but that's maybe a different story. And then a bunch of them also found in materials project, although there's a bit of a question with disorder. Crystallographers still haven't figured out what to do with disorder, but so we'll leave that just for now, and I'll move on to the next part. Yes. So in the COD, the Open Crystallography Database, there's a list of supposed duplicates. They call it possibly repeated, I think, something like that. And what they do is they just look for the same unit cell and the same composition, the exact kind of method that we're saying is a bad idea. And we found these pairs of structures. So on the top, same unit cell, same composition, different. And on the bottom, we have different unit cell, same composition because it has to be, but different unit cell, and they're the same. And you don't find that on the duplicates list. So whatever they're using for this duplicate isn't a great way to do it. We think we have something better, or at least something that could check whether these are really good. And then here is the results of our big experiment comparing crystals. We found that the CSD and COD overlap by a lot, which is to be expected. Crystallographers upload their data to both, and there's a percentage of redundancy in nearly all of these databases, meaning you can literally just get rid of a bunch of structures and you'd have the same number of unique structures in there. And now I'm talking about geometry plus atomic types as well. This required the atomic types of each site to line up, not just for the geometry to be the same. And this was done quite quickly, and we later verified it with PDD squared, at least for ICSD and MP and genome. The structures we said were equivalent are equivalent. Okay, so now there's some maps. I'm going to kind of rush through these maps because I would like to get onto the demo of the software, which is supposed to be the prime thing. But what we're looking at here is 4 databases on the heat map in the background. Obviously, everything really likes to live in that dark spot in the middle. And then on top, I've superimposed calcium carbonate polymorphs. And as we kind of hope, the 3 different polymorphs are separated into 3 distinct places. And these other things in the middle are theoretical polymorphs or phase transitions, or occasionally it's a structure where they didn't write down one of the atoms or gave it like a question mark for a label, something like that, right? But generally it's all separated. And it's similar for like carbon here. So diamond lives in its own little spot. There's very little variation, wiggle room in how diamond can be. So it lives in quite a tight spot. Graphite is different, and you can change the distance between the layers. And so it lies in kind of a bigger thing. And then phase transitions are right in between it. That's similar for boron nitride, which forms the similar kind of structures to diamond. You see that the graphite forms occur in roughly the same place as the boron nitride graphite forms, and diamond forms in the same place as well. And I think I will skip this slide and go straight to here, but I will get onto this more in a minute. So we notice on this, say that there are lines, and I'm actually going to investigate these lines live, how I would do it. But what was interesting about this was that we found this artifact down here with very, very regularly spaced blobs of, you see, those aren't individual crystals, they are blobs of crystals. But it looks almost as if some kind of grid search was used to generate the crystals. Very suspicious. If you click on these crystals, they're all generated by the same person, and it's just like regularly spaced geometry chosen in a grid search clearly. So this was a nice little find as well. And I will leave this for now because I want to get onto the demo, which will explain it a bit better. Actually, I'll run it and then maybe yeah. So in this case, what we have, if you remember, I mentioned we subtract the asymptotic from the AMD, and we get this nice wave. If you divide by it instead, then everything that's equivalent to up to uniform scaling. Yeah, everything that is equivalent up to uniform scaling gets shrunk down into 1 point. So all like the simple cubic structures all get collapsed down into exactly 1 point. And so we don't have the same lines that we had in the previous plot of the materials project. All these lines point towards the origin and are due to uniform scaling. In this plot, we have the lines, but I'll explain what these lines are because they're not about uniform scaling. Everything on this plot has been, that's up to uniform scaling has been collapsed down. So let's do a little demo while I've still got a little bit of time. So I'm going to plot the ICSD here, and this is the Geomap software. So I quite like the 3D scatter plot, which I can't show quite as well on slides, so I'll do that, and I like this fly camera. Now I'm going to choose 3 values of K here. If you're wondering why I'm choosing these, it's because they're uncorrelated values of K generally, which is what you'd want. And yeah, let's do this. So we can try coloring by like density. This is going to be like a demo. This is how I would do this if I was actually like trying to investigate this. So I think Zoom is making this run slow, but it's okay. So I'm flying up to this cloud. We can see it's washed out, right? Because some high density structure somewhere is completely washing this out. So how do we sort that out? I can split right here and give myself another plot area. I'll copy over. I want to do the ICSD, but I want to do a quick histogram of density. just so we can get a decent cutoff value for density. So we can see something. You can see there's some really, really dense structure, like ridiculously high density. So, so if we just zoom in, if we choose something like 20, like as a filter, that should be okay. So let's close that. I can add a filter here, go density smaller than 20, and that should improve the coloring. Okay, much better. So yeah, I have to control the velocity of the camera here. It's a little difficult. Okay. Okay, so I usually use this in dark mode, not light mode, but okay. So we see these lines that are, I'm kind of rotating myself around. So you can see these lines, which are all points to the origin, like this one. Let me zoom in on this one and hover over it. You see here, watch the ABC right here. The fifth one down. If I just move the mouse up this line, that ABC, steadily goes up and up and up and up and up, right? So these are cubic crystals. Yeah, These are cubic crystals which are all equivalent up to uniform scaling, and it's changing that continuously, right? And if you go to these other lines as well, you'll see that they're mostly cubics. Like if I hover over something in this line, that's also a cubic. So if we suspect that these lines are mostly cubics, we can add a filter and ask for only crystal system cubic. Okay. By the way, this app has been crashing like quite a lot, and I have no idea why. So if that happens during the talk, then it will happen. But just to warn you. All right. So this is just the cubic crystals. I'm flying around this universe of cubics. Whoa. Trying to slow down the camera. There we go. So now we've kind of isolated these lines. You can click on a structure and bring it up in the structure viewer and see what it looks like if it will load. My laptop is under quite a bit of stress. So all these structures on this line will look like this, but uniformly scaled. How do we isolate these lines? I'm worried about time here. So what I will do is I'll do this. We could try, first of all, I could press this copy button and it'll copy over the data selection with the filters. We could do a bar chart of, let's do parent space group. So space group is what you might know. Parent space group is the space group you get if all the atoms were the same type. So because sometimes symmetry breaks just because of atomic types, right? Now I'm going to zoom out on the left a bit here and see what happens when I hover over these categories. So if I do that, I can see what's highlighted on the plot. You see there's a line in the back there that's clearly associated with that. That's space group 229. This is 227. So 227 is this stuff in that line, plus some other stuff as well. There's other lines in there. So one space group doesn't correspond to line, and vice versa. You see that some of these lines have go back to multiple space groups. There isn't a perfect one-to-one correspondence here. Instead, I can use this isotropic normalization thing that we were using earlier. So let me use a heat map here, and you'll see why. This is the isotropically normalized version. You choose the same K values as the other plot. No, any qubit, anything. Yeah, anything space group number above 195, yeah. So here, we've got a nice heat map. This is isotropically normalized. If you're wondering why the color scale looks so bad, it's not for the same reason as density. It's because these cells contain lots of points. These lines on the left all get collapsed into single cells. So if I hover here, you can see it highlights one line on the left. If I hover over a different point, like this one, it highlights one line. So this really nicely isolates the different lines that are present because they all get collapsed down into one point, and these one points become very hot spots on that thing on the right. Okay, so now I would like to do at least one final thing because I think this is exciting, okay? So I'm going to look at this artifact over here, which I only figured out what it was on Sunday. In fact, I'm going to, whoops, it's not select item, I want to, so you can see it a little better, if I can do this. Up the size to about 2. but hopefully you can already see this artifact I'm going to talk about, this weird spectra of lines. I'm just increasing the size of points here, so it's a little easier to see there. Got to fly up, fly up, fly up, fly up. Okay. Here we are. We've got this clear artifact here, right? What is going on here, right? It's a little strange. In fact, if you hover over these, I could. These are all space group 227, so I could but we've got our eyes on this artifact here. So what are we looking at? I actually just guessed, and I wonder if anyone can guess here what we are looking at. Not what crystals we're looking at, but why do we see this weird spectra? Why do we have these lines? We know why there are lines pointing towards the origin. That's uniform scaling, but why are they like this?
Some aliens in the crystal universe.
No, definitely not. Definitely not, unless the aliens are humans. So what we're looking at are decimal places. Okay, so these are all spinels. Spinels I have this written down here. A metal at, so in fractional coordinates, they have one metal at 1/8, 1/8, 1/8, another metal at 1/2, 1/4, 1/4. And then they have an oxygen at 1/4 plus epsilon, 1/4 plus epsilon, 1/4 plus epsilon. So this line on the left here is when epsilon equals 0. The next major line, so you see this major line separated by minor lines, the next major line is an increase of 0.001. Because most SIFs write down their fractional coordinates to 3 decimal places. So what you're looking at is just the fact that people record 3 decimal places. And the little lines in between is that some people record them up to 4 decimal places. So there's just this one element that's just moving, this oxygen, but it doesn't move smoothly because nobody writes it down to many decimal places. And that's what gives us this artifact. The only thing I can't explain is why there's this like kink. Can you see like it's planar and then it goes up? I have no idea why that is, but it's there. So yeah, we can see the continuity really well with this particular thing here. And I think I wasn't going to end on that. I want to do one more thing if I've got like a little bit of time. So okay, so let's switch to isotropically normalized. And I'm going to use slightly different values of K just because I actually know where it is, but these are uncorrelated as well. We could color here by parent space group, I think. Get rid of these filters and let's look. So if you remember, this isotropic normalization should take these lines and collapse them into points, the lines that were there because of uniform scaling. But there were still lines on those plots. So why are there still lines on the plots? I've identified one area where we can just go. So look at this orange area here. We've got this very clear vertex, and then it like splits off in 2 directions, which are very clearly linear. And if you look really hard, there's kind of a third direction it splits off in. So why are these lines? Well, if we click, we can just see what's at the vertex. It's a perfect face-centered cubic. That's all things that are face-centered cubic, regardless of scale, will be at that point. If we go just slightly off of it, I have to find a good one, a good example here, because they're not all written down the same way. I think this will be okay, maybe. Yeah, so look at this. Face-centered cubic, right? Well, if we look at ABC, A is equal to B, but it's not equal to C. So here is when A, B, and C are equal. If you start stretching C, then you go off in this direction. If you squash C, then you're going off in this direction. And the secret third direction is due to disorder, which I haven't mentioned, but the way I've implemented disorder means that if you just take this structure and then one of these metals or whatever it is has a fractional occupancy. So sometimes the site is vacant, sometimes it's there. If you continuously change that occupancy, it corresponds to a straight line on this plot again, which is quite nice. And I only discovered that was the case recently. So the lines on these plots, which are sometimes curved, correspond to so far either non-uniform scaling or continuous change in occupancy of atoms. So I'll leave it there because I'm right about on time, I guess. Thank you very much.
Yes, thank you, Dan. Great presentation. Yeah, please keep it. Yeah,
Sure. I see it's a bit noisy, but